An application of integration would be to use the shell method to find the volume of a solid as it's revolved about an axis. If we take a function here, and we'll just call that function f of x, and let's say we want to rotate this function about the y-axis here, the vertical axis. Then with the shell method, what you're doing is you're creating concentric shells starting from a lower limit and going to an upper limit. So let's just say we want to start here at location A, and we'll make location A right on the axis of rotation. And we'll go to the upper limit, which is B. And in this situation, if we're going to create concentric shells, what we're going to do is we're going to have an incremental rectangle here that is going to be parallel to the axis of rotation. So if the axis of rotation is the vertical axis or the y-axis, your incremental rectangle is going to be vertically oriented, which means that the thickness of the rectangle here is going to be a dy, or excuse me, I said that wrong, a dx. The incremental thickness is going to be a dx here. So as we rotate this incremental rectangle around the y-axis, what we have then is we have this hollow cylinder here, almost like a soup can or a paper towel roll or something like that. And so as we stack these incremental cylinders from the lower limit to the upper limit, they start to fill in that solid and create that solid of revolution. And so if we think about this, then we know that since this is a hollow cylinder, we have an outer cylinder and we have an inner cylinder. And so looking at that, of course, the volume of that cylinder, then if we're looking at it, we're looking at basically that surface area, which is going to be the perimeter of the base times the height. So we're looking at an incremental volume here, which is basically going to be the area times the incremental thickness, which is that dx, which is the dx. And so this surface area is going to be the perimeter of the base times the height times dx. And so the perimeter of the base is going to be this, which is 2 pi times the radius. So if we look at this, if we just write it the way we would in geometry, 2 pi times the radius, then that radius is going to extend from here to here. And so that radius then becomes that just the variable x, and the height is the value. The height of the cylinder would be the height of this rectangle, which is the value of the function. So this radius then is just x, and that we give the variable p of x. And the height then just becomes the function, or the f of x, and that we give the notation h of x, and that really is just f of x. And so we end up with an incremental volume then that looks like 2 pi p of x times h of x dx. And as we accumulate all of that from A to B, then we get this expression here. that says that the volume is the integral from a to b of p of x times h of x dx times 2 pi. Taking the concept of the shell method into this problem here, where we are going to accumulate concentric hollow cylinders, we're going to take this about the y-axis. So just like we did in our example, our conceptual example. So we're going to rotate this about the y-axis, and this is where drawing the incremental rectangle becomes, I think, pretty important, so that you can appropriately label things. So if we look at that incremental rectangle, we're going to, again, remember that rectangle is taken parallel to the axis of rotation. Some people will say that shell rhymes with parallels to kind of help you remember that you're drawing that incremental rectangle parallel. We know it's a dx problem since the thickness of that rectangle is along the horizontal. And then we can start labeling our p of x. We know our p of x goes from the axis of rotation out to the rectangle. So we know our p of x is located here. We know this is our h of x. And so from the diagram here, we know then our p of x is just the coordinate x. It's just measured right from the y-axis, which is the x equals 0 location, and our h of x happens to be the function because it starts at the x-axis and goes up to that red line, and that red line is 1 minus x. So we know the h of x is 1 minus x. So putting this into then the expression for the volume, we're going to go from 0 to 1. And we're going to have 2 pi, which I could pull out. I'll pull that out in the next step, times p of x, which is x, times h of x, which is 1 minus x dx. And so we have this expression for the volume. And I'm going to go ahead and distribute that. So that's going to be x minus x squared. Now I need those brackets. And that's easy enough to integrate. So we can go ahead and integrate this one by hand. Integrating x, we get x squared over 2. Integrating x squared, we get x cubed over 3. Whoops. Let's get rid of that. There we go. X squared over 3. We're going to evaluate that from 0 to 1. So we are looking at plugging 1 in here. We get 1/2 minus 1/3. Plugging 0 in for both, we get minus 0. And a half minus a third, don't forget there that the common denominator is a 6, so this is really 3 over 6 minus 2 over 6. So that's 2 pi times 1 over 6. And so that is pi over 3 for the volume. And you might notice as you rotate this around the x-axis, what you're really getting is a cone. Ooh, that's a terrible cone. Let me try that again. You're getting a cone. That's a little better. Okay, with a height of 1 and a radius of 1. So we have a height here of 1, and we have a radius of 1. And if you remember the volume equation from geometry, volume is volume of a cone is 1/3 the area of the base times the altitude. And of course the area of the base being a circle, is pi radius squared times the altitude. And when we plug in 1 for the radius, and we plug in 1 for the altitude, you notice we end up getting pi over 3. So really, this is nothing more this one in particular, is nothing more than a geometry problem. And if you see it as a geometry problem, there is no problem with just using geometry. If you remember it, you don't have to use calculus in that instance. You may also recognize this one as a cone as well. It's just inverted. And so if we revolve this, this triangular shape about the y-axis, we just get this inverted cone here, kind of like one of those cups you drink out of at one of those coolers, those water stations. And so you might notice that the height of this is 4, and the radius here looks to be about 1 1/3. I'm willing to guess if we set those two functions equal to each other, we'll get a point out here that is, I believe, 4/3, 4. And so you could use geometry again to solve this. I'm going to use calculus though, just to kind of show you what has to happen here with an inverted cone from a calculus standpoint. We're looking at the incremental rectangle that looks like this. And if you notice, the incremental rectangle does not come down to the and touch the x-axis except for right at the beginning here at x equals 0. And so for this situation here, we still have a dx. So we're still looking at a dx problem. But the height here is going to be, well, let's see, the top of the rectangle is up here at 4, and the bottom of the rectangle changes depending upon its location along this line. So we have to take 4 and subtract this. And this happens to be 3x, the function that's in red here, and the function that's in red is this oblique line, and of course the function that's in blue is the horizontal line. So this this h of x here is not just the function, it's 4 minus 3x. I'll get a height of 4, and we have to subtract off the function 3x. So and then the p of x is still, we're still measuring over from the y-axis, so your p of x is still just x. Okay, so knowing that, h of x is 4 minus 3x, we can go ahead and set up the expression for the volume here. We're integrating from 0 to 4/3. We do need that that upper bound there, and that we get by setting 3x equal to 4, setting the two functions equal to each other. So x equals 4/3. And so we've got 2 pi here. And our p of x is x, and our h of x is 4 minus 3x, dx. And so integrating that from 0 to 4/3, we get our answer. And I'll let you do that on your TI-84. But when we integrate that, we end up getting an answer of 64 pi over 27 for the volume of that inverted cone. For this last method, what we're going to do is we're going to rotate about a line parallel to the y-axis, but we're going to offset it. We're going to rotate about this line here, x equals 2. And so we're going to rotate the intersection of these two quadratics, the red quadratic being 4 minus x squared, and the blue quadratic being x squared. And so when we look at the intersection here, we're looking at this green region. And so it gets a little more complicated here. So we're going to look at this green region and rotating this green region about the line x equals 2. So when we look at this, the incremental rectangle looks something like this. And again, if you notice, it doesn't come all the way down to the axis, so we're going to have a little more complicated h of x function. Our p of x is always measured from the axis of rotation back to that incremental rectangle. So if we look at that, the p of x is actually measured here. So there's our P of x. P of x is always that horizontal distance back to the axis of rotation. It's got to be back to the center of the solid, basically. And so that distance then is going to be a more complicated expression. We know the distance from here, the y-axis, to the incremental rectangle is just x. So we know that coming out in this direction, we have the value x. We're just measuring from 0. And of course, coming out to the axis of rotation is 2. So that makes P of x then, that leftover portion right in here. So it's going to be 2 minus x. So that's going to be our P of x. Our h of x, again, is also going to be a fairly complicated expression. Our h of x has a top on the red function and a bottom on the blue function. So that being the case, we're going to have to take our red function and subtract our blue function. So what that's going to look like is taking our red function, which is 4x minus x squared, and subtracting our blue function, which is x squared. And so when we simplify that, that is 4x minus 2x squared. And so there's our h of x function. And again, this is why I think it's so important to get that incremental rectangle drawn, get that P of x and that h of x identified on the drawing. So identify this h of x here. And get these expressions written even before you start any calculus. I think it's just a really good organizational tool. So to write the expression now for the volume, it just really is a matter of plugging this information into the formula. We know we're going to integrate from here to here, so that's going to be from 0 to 2. And our P of x, let me just rewrite that because that 0 is too sloppy for me. From 0 to 2. There we go. And then it's P of x times h of x. So it's 2 minus x times 4x minus 2x squared. And that can be FOILed. This is the expression for the volume. And this is just a polynomial. You can FOIL this out and then integrate it pretty easily. And you certainly would be expected to be able to do that. But I'm going to just use the TI-84 and the fint capability to integrate this, just for saving a little bit of time here. So I'm going to put in the two functions into y1. So there's our 2 minus x function. Here's our 4x minus 2x squared function. And I'm going to use the vars capability to make our expression, our fint expression, a little more simple. So if I go into math 9 to get fint, and so this is our y1, this is our y2, they're multiplied together. So I'm just going to go ahead into vars and into yvars function and grab y1 and then multiply, hit the multiply sign, go back into vars function and y2. So now I have y1 times y2. That represents these two functions being multiplied together. The variable of integration is x. That's what's written in y1 and y2. And we're going to integrate from 0 to 2. And remember, this is just the expression for the integral, so we have to include the 2 pi in our answer. And that ends up being 2.6 repeating. And if you want a decimal equivalent for that, we can just hit math and fraction. And so it ends up being 8/3. So we have 2 pi times 8/3, which ends up being 16 pi over 3 cubic units for the volume of that solid.